at least. So I'm very happy to be the chair of this session. And the first speaker will be András Gyenis, and he will talk about experimental realization of the soft 0-pi superconducting qubit. This is work he has done at Princeton, and now he's at the University of Copenhagen. And please, whenever you have a question, type it into the chat that we can discuss it after this 25 minutes presentation.
Hi. Thank you very much for the invitation. And I'm very excited to talk about our experimental work on this new type of superconducting qubit, which we called the soft 0-pi superconducting circuit. And the work was done in Andrew Haug's group at Princeton University. And if you would like to read more about these results, you can find our paper on arXiv under this address. It is, yes. Okay, so now it's working. Sorry about this. So it is well known, if we want to build a robust quantum computer, then we must have some sort of quantum error correction built into our architecture. And there are multiple ways to do it. For example, we can encode the quantum information into a collection of physical qubits, or we can use a harmonic resonator and its higher lying levels in order to redundantly encode the information. And the focus of this talk is an alternative approach where we use some sort of passive error correction or hardware level protection when we build a superconducting circuit where errors are energetically unfavorable. So the protection happens on the hardware level without using any local quantum gates or measurements. And this idea dates back pretty much to the beginning of the field. And since then, there has been two major directions where this idea developed to. First, if we use a large array of Josephson junctions, and we make this array really large, so the unit cell n goes to a big number, then we can end up with a two-fold degenerate ground state, which is protected against dephasing. And more recently, there is another proposal to achieve such doubly degenerate ground state and protection for superconducting qubits. And this is based on the idea of protected compact qubits when we use a circuit which only has a few degrees of freedom, but at the same time, its energy scales are quite large or quite small. So the energy scales are extreme. And for example, in this case, on the right, you can see the 0-pi qubit, which can mimic the circuit on the left, which is the current mirror circuit, in case the inductance of this qubit is large enough and some other requirements are satisfied. And before I dive into the physics of this 0-pi circuit, let me just make a definition that what we mean by an intrinsically error-protected superconducting qubit. And in our definition, a protected qubit must be protected in T1 and T2 simultaneously. So with other words, it has to be protected against energy relaxation and pure dephasing at the same time. And let's see how we can achieve this. So let's start with T1 protection. And this can be achieved based on the concept called wave function with disjoint support. And the key idea of this concept is that we use qubit wave functions which are localized in different locations in the configuration space. Like loosely speaking, only the tail of the wave functions are overlapping. Now, if you take any sort of matrix and any sort of operator and calculate a matrix element between these two qubit wave functions, this matrix element is going to be exponentially small. And if you recall Fermi's golden rule, such small matrix elements will lead to very large T1 values. And such situation can be realized by using a double well potential, for example. To achieve protection against pure dephasing, we have to do something very different. We have to make the energy levels as a function of some offset parameter flat. And that is because dephasing arises from the fact that the energy levels change, or the energy of the qubit changes as a function of offset charge or external flux. So in order to avoid that, we have to make the qubit levels insensitive against the external parameter. So note that we don't need degeneracy, we only need flat energy levels. And a special case of this situation arises if we use a first order protection. It means that we have to tune the external parameter to a specific value. And if we tuned the qubit there and the noise is small enough, this first order protection also very good and can enhance the qubit lifetime significantly. So let me just show you two examples how we can make such protection in superconducting qubits and how can we create insensitive levels. So the first example is a charge mode, or a charge-like qubit when you have a Josephson junction, which is shunted by a pair of capacitors. And this qubit couples to other offset charge and G with the charge operator and linearly. So you can get charge insensitive levels if you delocalize your qubit states in many charge states, because effectively then the fluctuation in the offset charge is gonna average out. And in terms of parameters for the qubit, what we need to do is we need to build a qubit with a large capacitor. And we like saying that this is a heavy mode. So in order to make a charge qubit charge insensitive, we have to make it heavy. And that comes from the fact that capacitor and mass plays very similar role in a Hamiltonian. Now, and a very good example for this qubit is the very well-known transmon. Now let's look at what we have to do with a flux-like qubit, a flux mode. This device couples to the external flux linearly with the phase operator. So now what you have to do is delocalize the qubit states in many flux states. And since the phase operator and the charge operator are somewhat conjugate variables, actually you will need to do exactly the opposite what you would do for a charge-like device, since in a flux qubit, you need to have very small capacitances in order to make it charge, in order to make it flux insensitive. And in addition to that, we also have to make the inductance very big. But the take-home message here, if we want to build superconducting circuits which are charge insensitive, we need a heavy mode, and superconducting circuits which are flux insensitive, we need a light mode. And that's the thing what we can do when we are designing a qubit. But there is another important ingredient for protection against noise, because we have to also take into account what we are fighting against. And there is a very big asymmetry here, because flux noise, it's roughly 2 orders of magnitude smaller than charge noise. So now we could even think that maybe it's better if we just focus on flux-like qubits, because the noise which we are worried about is much smaller. But what nature gives us actually takes it back, because it is trivial to build big capacitors and make a charge insensitive charge mode, but it's really, really hard to make a qubit where the capacitance is very, very small. It requires some very advanced fab, and there has been some nice results recently this year which achieved such regime. But in a normal cases, what we can do easily in a lab is charge modes with exponentially suppressed offset charge sensitivity, and flux modes with only first order suppressed external flux insensitivity. But at the end of the day, the charge noise is much bigger than the flux noise. So the two type of qubits perform roughly to the same level. So far, I only talked about protection against dephasing. And the other very important thing we have to discuss is protection against energy relaxation or T1 protection. And that's a very interesting question, because if we look at like a charge-like device where we have only one single minimum in the potential, we are unable to make disjoint states because there is only just one value where we can pack in the qubit wave functions. For flux-like devices, the situation is a bit more interesting because you have multiple values in phase space, so you can actually localize your qubit states in different values and get very good T1s. But that actually contradicts what I talked before, that we need to delocalize states in order to get high T2. So with these single mode devices, we are stuck with this situation that we can get either very good T1 and bad T2, or good T2 and bad T1. And that's actually the case. With single mode superconducting qubits, we cannot be simultaneously protected in T1 and T2. But the good news is, if we start increasing the number of modes in the circuit, we can overcome this limitation. And the simplest case to do it is just combining a heavy charge mode with a light flux mode. And this device is actually the 0-pi circuit, which can offer protection in both T1 and T2. So now let's take a look what we mean by combining a heavy charge mode and the light flux mode. So on this first image, I drew heavy charge mode because we have two Josephson junctions and two big capacitors. Now we can also draw a flux-like mode where we have only Josephson junctions and big inductors. And now if I connect these two devices together in a smart way, then I can actually get a 4-node device, which is the 0-pi qubit proposed by Brooks, Kitaev, and Preskill. And there is one catch in this method, because by doing that, we also introduce the third mode to the device, which is a harmonic mode. It doesn't contain any Josephson junction, and it is low frequency, so it complicates the device performance. Nevertheless, the 0-pi qubit can be decomposed to these three modes: the theta mode, the phi mode, and the zeta mode. And what we can do in the lab is build this circuit topology, but we cannot achieve the originally proposed parameter regimes, exactly for the reason what I discussed before, that we cannot make capacitors disappear. So that's our qubit, is the soft 0-pi circuit, which is equivalent, the circuit topology is equivalent to the originally proposed 0-pi circuit, but the main difference is that we are only first order protected against flux, and at the same time we are exponentially protected against charge noise. And actually, this is not that bad of choice, and because the flux noise, as we talked about before, much less than the charge noise. So actually, a first order protection can behave very well. We can also look at the qubit, how it behaves if we draw the potential, the two-dimensional potential. And it is actually indeed the combination of a charge-like device and a flux-like device. And if we want to name it a bit More precisely, it's a combination of a transmon and a fluxonium. And that can be seen if we look at the potential from the flux-like direction, that's phi, because what you can see is a quadratic potential, which is modulated by a cosine function. And that's exactly how a fluxonium potential looks like. Now, if you look at from the theta direction, which is the transmon direction of the qubit, you only see a cosine-like potential, which describes the transmon. The qubit states are disjoint, and the 0 state is located in the 0 valley, and the 1 state is located in the pi valley. Now, this duality also appears in the qubit when we investigate how it behaves against external flux and charge. On the left picture, I show the energy dispersion of the sub-zero pi qubit as a function of external flux. And if you are familiar with fluxonium, then you would immediately say that this is exactly a fluxonium energy dispersion. And that's pretty much true. And you can also find transitions which we call plasmon transitions when we excite the qubit states in the same valley, or when we go between the 0 and the pi valley, we can see fluxon transitions. And in addition to that, we have a first order magnetic sweet spot at 0 flux where we operate the qubit. Now, if you look at how it behaves as a function of gate charges, you can see that the dispersion is very flat, so it is insensitive against charge and exponentially insensitive. The qubit wave functions are two-dimensional, and they are located either in the 0 or in the pi valley, and they have this some sort of anisotropic harmonic oscillator wave functions. The nodes appear along the heavy direction first, and then at high energy, you can get the phi plasmon behavior as well when the node appears along the phi direction. If you look at the wave functions in the pi valley, you see a similar behavior, but everything is doubled because there are two minimum in the pi valley. And we use the lowest lying states in the qubit as the 0 and the 1 state, the lowest lying states in the 0 and in the pi valley. And the other important energy level in this qubit is level 9. And this is somewhat a magical energy level because it is charge insensitive and still located at very high energy. And it is coupled to both the 0 and the 1 states. So it can be used as an ancillary state. We built this qubit in a two-dimensional architecture, and we coupled it to a resonator capacitively. And here you can see a zoom in on the device itself. And the most surprising thing which you can see on this device is that we had to use this strongly interdigitated capacitor structure. And the reason why we did that is because we had to decrease the footprint of the capacitor itself. And because we wanted to have big capacitance value between certain nodes, and we wanted to have very small capacitances between other nodes, since we have to combine a heavy and a light mode in the very same device. In addition to that, you can also see the Josephson junctions in the zoom in and the superinductors, which were made out of an array of Josephson junctions. We mapped out the spectrum of this device using conventional circuit QED measurements. You can see here it as a function of external flux and as a function of gate charge. And the spectrum looks very rich, and there are many, many energy levels, but just using a two-mode 0 pi Hamiltonian, we can understand every single feature in the device. And that's true up to level 17 over 12 gigahertz. One thing which might be also surprising that we actually don't see in the spectroscopic data the 0-1 transition. There is no signal here where we would expect the actual qubit operating point. But that's actually a good news, because we remember that we built a qubit where the 0 and the 1 states are disjoint, so transition between these states are not allowed. So the qubit is protected against energy relaxation, but at the same time it's protected from us to measure it. The way we can overcome this is using this already mentioned level 9 state, which is coupled to both 0 and 1 state. And if we go like 0, 9, 1, we can do a coherent control of the device. But before I talk about that, I just would like to show you how we can really prove that there are states there, even though we don't see in a normal spectroscopy measurement. And the method which we used is called Adler-Tann spectroscopy. And the key idea here is that you have two levels, 0 and 1, which are not coupled to each other, but they are coupled to level 9 at the same time. Now we apply a drive on this system and create addressed atom states. And when this drive, which we call coupler drive, is on resonance with the 9-1 transition, we will see a Rabi splitting of the states, and these Rabi split states are called the Adler-Tann doublet. And then we add a weak probe to see the appearance of this doublet. And the way it looks like in a measurement is that we vary both the coupler and the probe frequency at the same time. And when the coupler is not on resonant with the 9-1 transition, we only detect the 0-1 transition. And when it is on resonant and it creates the Adler-Tann doublets, then we will see an avoided crossing. So we went ahead and did this measurement in our device. We applied a very strong coupler drive in the pi valley and a weak probe drive in the 0 valley. And this is the result of the measurement. You can see the spectroscopy signature of level 9 at 8.1 gigahertz. And when the coupler is on resonance with the 9-1 transition, we can see the appearance of level 1. And in addition to that, we can also see level 2, which is the anti-symmetric version of the logical 1 state. Now we can do this as a function of external flux, and that's what you can see here on the right. And what is important here is that at 0 flux, we see a first order insensitive point in the device. So that's the first important thing about our circuit, is that it has disjoint wave functions. So it's protected against T1, and it has insensitive levels, at least first order protected against flux and exponentially protected against charge. And in that sense, this qubit is protected. Now, I don't have much time to go into details, but I would like to spend a slide on level 9, because this is a very interesting feature of this device, which we were not expecting before we built it. So we are coming from the transmon world, and there, if you go up to higher and higher energy levels, your charge dispersion gets worse and worse, or it gets bigger and bigger, with other words. That's not the case in the 0 pi qubit. In 0 pi circuit, or in the sub-0 pi, also in the sub-0 pi circuit, level 9 is charge insensitive, although it's located at a very high energy. And the reason for that is that this state is anti-symmetric, considering the flux mode. And that eventually reduces the charge sensitivity of this level. And this is a critical point in order to make sure that we can operate this circuit as a qubit because we have to rely the coherence time of this level 9 for coherent control. So this stable ancillary level at high energy is the second important feature of the sub-zero pi circuit, which allows us to do coherent control. Since if your higher lying level is very charge sensitive, for example, level 8, which you can see here below level 9, you wouldn't be able to use it as an ancillary level because the coherence time is just too bad. Now, let's talk about how we did the actual gates on the qubit.
So you have like 1 minute left or so.
Oh, okay, that should be enough. Yeah. So the way we do coherent population transfer on this qubit is basically applying two Gaussian pulses which are overlapping, and on the right you can see a numerical calculation how the population of 0, 9, and 1 state should look like as a function of the amplitude of Rabi amplitude of these two drives. And the take-home message here is that if you are at 45 degrees, so your Rabi amplitudes are equal, then you can do a very good Rabi fluid between the 0 and 1 state. And we did this measurement, and that's what you can see on the left. And this is and also we did it as a function of detuning, which can be fit very well with an effective Raman theory. And this is the last point which we had to satisfy in order to have a qubit that we can do coherent population transfer between the states. And we measured finally the T1 and T2 of this device, which you can see on the left. T1 is 1.5 millisecondum, T2 Ramsey is 9 microsecondum, and T2 echo is 26 microsecondum. And an obvious question arises that what limits our T2? At this point, we are not sure. The two quantities are either photon shot noise arising from the presence of a harmonic mode, or maybe the flux noise is still too bad because our sweet spot is not big enough. And I would like to acknowledge my collaborators, Pranav and Tom, who worked on the experiments, Augustine and Julian, who gave us the big theory support, and the main PIs on this project was Dave Schuster, Jens Koch, Alexander Bley, and a big thanks goes to Andrew Haug. And I will leave up my conclusion slide up here, and looking forward to questions.
Thank you very much for this exciting presentation. And also, you seemed in your last slides almost to anticipate any question I would have asked and answering them. There are a few more questions in the chat. The first one is about the level 9 you use for control. So you described nicely how it's charge insensitive. Is there also something to mention about the T1?
Of level 9?
Yeah, of level 9.
So the T1 of level 9 is not good. That's below a microsecondum or around a microsecondum, because it can decay to so many levels at the same time.
So is this in any way limiting your Rabi flop at the moment?
Yes, it could be a limiting factor, but because although we are doing this Raman gate, which you can see here, we do occupy level 9 a little bit, so that can reduce the fidelity of the gate, and also it can reduce the fidelity of the gate itself.
Okay, yeah. Thank you. So I guess we can go a little bit longer and take one more question from the chat. So it's about what's the frequency of the harmonic mode? Can one see it, and spectroscopically, and what's its thermal population?
Yeah. So it's around 700 megahertz, and we can see it in the spectroscopic data. it shows up as a resonance frequency. And well, the thermal population is goes like we assume that the chip is around or the qubit itself is around 50 millikelvin, like that's what people usually find. And that would lead I don't have an exact number like what thermal population that would lead right now, but in terms of limiting factor, that can give you around 100 microsecondum, roughly 100 microsecondum limit on the qubit performance.
Yeah, thank you very much. I think the last question is also about the level 9, but we can further discuss it in the Slack channel, and anyone else is welcome to ask questions there. And then I would move on to the next speaker, which is Elliot Qubit. Can you, hello?
Hey, you all hear?
Can you share your slides? So Elliot is speaking about the very small logical qubit, an alternative paradigm for bosonic error correction, and he comes from the Colorado School of Mines. Excited to learn more.
Thank you. And so just real quick, can you hear me and see my slides?
I can hear you and see your slides.
Okay, good. Hi, everybody. So thank you all so much, both to the organizers for inviting me to present during this and to everyone in the audience.